Testing, testing, 1, 2, 3, testing, testing. Good, that seems to be working. Yep, fair enough. I don't know, what's poppin'? A quiet whistling. Yeah, I imagine the university is probably even more deserted than it usually is in the summer. Not surprising given everything that's been going on in the world so far. I can't really hear that quiet whistling that you were talking about. Not sure if that's on my end or not. Well, the time is currently 12:30, so we might as well get started then. So, those of you who paid attention to the beginning of the last live stream, there was a considerable amount said about the VPN being an insubstantial ghost of its former self under the current load conditions. And as a result of all of that, we are having to find alternative ways of going about getting the assignments submitted. Okay, cool. The other thing, I actually listened to yesterday's lecture back again, and it seems to me that I use the word way too much. It is a terrible bad habit, and I will try to avoid using it in the future. So if you hear sort of these awkward pauses, sort of is another phrase that I need to work on. If you hear these awkward pauses in my dialogue, then what I'm doing is I'm intentionally not saying So, oh, okay, good. Yeah. So, yeah, anyway. Bad joke. Anyway. A low whistling coming from your backyard, doesn't that usually mean that a shell is incoming? Like from a mortar cannon? Hopefully things haven't degraded to that point wherever you are, Moonstar. So, if you take a look at Avenue, you'll notice that I have, in fact, now published the policy document that I was discussing in detail during the last stream. It should be... I won't bother to go through with it. Yeah, really, right? I won't bother going through this policy line by line, as I usually do, as it's more or less exactly what I said during the last lecture, with, some slight modifications. There is a YouTube link to a video that instructs you on how to do this, rather than me actually typing out written instructions, which seems to be a reasonable way of going about doing this. There are a couple of notes from Eric with respect to what he'd like the naming convention to be. I see he's giving everybody my Mac ID as the example, but, You all know it because that's also my email address. Sorry. Okay, so this is the rule. Every time I use the words or sort of, like sort of this, like is another one, any of those filler words, people in chat, like, put a skull and crossbones into chat for me. That might be an interesting way to see if I can train myself out of these annoying vocal habits. Yeah, no, it might as well. The world might be ending, but that doesn't mean that we can't focus on a little self-improvement, eh? So, anyway. So, yes, you can review this document at your leisure. Seeing as we spent something like 20 minutes on discussing the course and the course policies during the last live stream, I don't see any reason to spend 20 minutes on it this time. So why don't we just move directly into our lecture material for today? Oh, jeez. Oh, can I? No, okay. It didn't work twice. Anyway, so, pardon me. Last time that we were talking about this concept of abstract classes. I'm not going to go over that too awful much, but essentially, if you have a class that is designed specifically for the purpose of use in inheritance schemes and is not necessarily designed for... Yep, thank you. If you have a class that's not designed for actual instantiation, but is rather designed to be inherited into other classes, and those classes might have instantiations that you could use, then we are talking about what is known as an abstract class. It's kind of an academic distinction. There's nothing inherent to an abstract class that makes it an abstract class. It's just kind of the manner in which it's been designed. So, there you go. Abstract classes. So, we're actually almost through this particular set of slides. We've got Mario coming up, folks. We've got a few more examples to do, which I'd like to go over in reasonable detail, even though you will hopefully, by this point, seen classes being shouldn't give you the answers, jeez. You guys will have hopefully seen classes being developed a number of times in tutorials so far, so this shouldn't be too awful much of a strain of your faculties. So, let's talk about our first concrete example for this, our third lecture live stream. Birthday calendar. So, the birthday calendar is a thing that keeps track of people's names and their birthdays. It's essentially a dictionary with some additional functionality built in. At least, a dictionary would be a cool way to do it. So let's review what functionality we require from it. We need the following operations in addition to the init function, which always has to be there regardless of what you're doing. We'd like a clear function, method. This clear method should remove all names from the calendar. We need an add method, which allows us to add a name associated with a date to our calendar. We would like a contains method, which it checks the calendar to see if the name that is specified is contained within the calendar. And we have a birthdays. This is harder than I thought. We have a birthdays method. The whole not saying thing is harder than I thought. What we want the birthdays method to do is to produce all of the names that have a birthday on the specified date. So, all of this obviously is going to require some sort of data structure, hopefully one that is reasonably searchable. It's because we're working with a class here, the data structure is going to be shared between all of these method operations, but this isn't, this is very nominal use of class notation. The class allows us to encapsulate operations on shared data structures. So, if you've heard of, this is very similar to the idea of, in chat. Yes, thank you. Could chat, are you guys familiar with stacks? Have you heard of stacks or buffers, like FIFO buffers? Yeah. Okay, I like this. The skull and crossbones things. This works. I like it. So, I'd like to talk about stacks a little bit in this context because it's a very good example. The stack, the definition of a stack with respect to computing, and stacks are sort of a type of buffer. So with respect to buffers, you have various types based on the manner in which data is extracted from them, given some relationship to the manner in which they were put into the data structure. Okay, thank you, Larry156. So you have things called FIFO buffers. So a FIFO buffer means first in, first out. This is a buffer in the conventional sense. The first thing that goes into the buffer is the first thing that is extracted from a buffer. Stack, no, that's, oh, I have comments. Lists with a size limit, essentially, or is that something else? That's not what really a stack is. Yeah, lists with it's no, not really. There's no hypothetical. You can have, conceptually, you can have something like an infinite stack or an infinite buffer. The difference between a FIFO buffer and a stack is a first in, last out buffer. So, as Larry156 is saying, you can sort of imagine it like a stack of plates, right? You take a plate and you put it in the stack, then you put more plates in the stack, but you have to remove things from the stack in the reverse of the order that they were put in. So you can only remove the top plate from the stack at a time. This is why they call it a stack. Another way of calling it, another thing you can call it is a first in, last out buffer. So there's really, with respect to the underlying data structure, any list or even a tuple or something of that nature, or even dictionaries you can do this with, as long as it's an ordered dictionary, all of these underlying data structures can be made to behave as stacks. However, what's different is the manner in which things are accessed. So you can construct a class for stack, for instance, that the push and the pop methods pushes something onto the stack, and pop pops the top thing off of the stack. These two methods they restrict access to the data structure in such a manner that the data structure has the properties associated with stacks. It's a reasonably simple example, and no, I'm not trying to fill time because we don't have many slides left. What are you talking about? So let's do stack before we do birthday calendar, because it's relatively straightforward. So in order to make a class for a stack, class stack, oh, not static, stack, there we go, inherits object, as pretty much everything will. So within this class, the first thing that you always want to do is you'll want to define an initialization function. See, okay, so here's the problem with speaking and me. When I have things in my brain, I want to get them out of my brain as fast as possible, and then I run out of words in my brain, and then I have these pauses. It's awful. Why are humans designed like this? It's terrible. Anyway, please register all complaints with the man upstairs. So let's define an initialization function. Def init. It'll take self, obviously, because everything does. And let's leave it at that. Let's take no parameters other than self. So we will define self dot s for stack is the empty list. So obviously this means that the underlying data structure that we are creating for the stack is going to be a list, which is a reasonable way of going about it, seeing as lists are mutable, and you need to have a lot of I know, I just did it. A lot of operations that change the size of the data structure. That's partially the purpose of the data structure. So, yes, if you believe in such a being. Yes, human beings, astonishingly anomalous. So, we can work with a list. We can define methods to access a list in such a manner that it turns it into a stack. So, let's define two methods. Define pop, taking self, and define push, taking self and some value v. So, going back to our plate analogy, when you push something onto the stack, you are taking the thing and you are putting it onto the stack. So, at this point, you have to decide whether you'd like what you have to decide is the exact manner in which the data structure is going to be interacted with. Personally, I think it makes it easier, slightly easier, rather than appending things to the back of the list as we push them onto the stack. Let's put things into the first position in the stack and sort of increase the size of the stack, grow it that way, if that makes sense. So, although I just realized that in the camera, my analogy will be reversed. Right, yes. We're not going to get into metaphysics. This is, if you want metaphysics, go take a theology class. Or a philosophy class. I'm pretty sure they do metaphysical stuff as well. Anyway, the reason that I'm making this particular distinction between sort of back appending and front appending, although I don't think that's technically accurate. In some languages, you have these very nice mechanisms for taking the last element in a list. Haskell is one of those languages. Python, it's relatively simple. However, if you want a better general purpose solution that sort of works for a large number of different programming languages that might not necessarily have the same ease of access as the back element. Well, anyway, you'll see it. I consider it a slightly more elegant example. So self.s is equal to self.s, and we're front appending the thing that we are taking as the input. Fine, good, excellent. So, prepending, yes, thank you. Prepending. So, with respect to popping a element, the interesting thing about popping is that it not only gives you what the top element is, but it also removes that element from the stack itself. So we're actually going to require 2 lines of code, 2 whole lines of code, can you imagine? So, self.s, well, it's interesting actually. The sort of intuitive way that you might go about writing this down is well, I'll illustrate. Self.s is equal to self.s from 1 to the end of the list. We'll take a slice of it. And then return self.s at 0. This is problematic because we need to make the modification to the data structure before we hit the return statement, because the return statement terminates the execution of the function. So we couldn't, for example, swap the order of these two operations. However, we do need to preserve what the first element in the list is before we make the modification. So this is the point at which you would introduce like an intermediate variable. X is equal to self.s at 0, and then we return X. Just the sort of slight day-to-day memory management type stuff that you have to keep in mind. So anyway, that implements a stack. Data nat equals 0. Yeah. Okay. So I have a question from chat. It's a doozy. Data nat equals 0 or successor of nat. Yeah, so you're talking about piano arithmetic. Is this a stack? Well, no. A stack is a data structure, and what you're doing right here is you're defining. Well, it has it comes from abstract algebra. So in order for it to be a stack, it has to have a push and a pop operation. You could define push and pop operations for piano arithmetic. However, there's nothing. I guess the problem that I have with it is that you're not actually storing any data inside of there. The data that you're storing inside of the piano arithmetic is the number of successor operations that have been applied to 0. Whereas in a stack, everything that you push or you pop from the object is a perhaps useful piece of data. These types of buffers are used quite often lower down in the operational hardware of the computer to synchronize keyboard operations and stuff like that. But yeah, no, a stack is a buffer. Buffers they're a hardware thing. They exist in hardware. Don't confuse the abstraction from the implementation. Right. Hopefully that answers your question. I have a question. Python does pop from the back end, not the front end. You have to pass the index 0 for the built-in pop function. Yeah, this is not the implementation of stack as it would be in Python specifically. This is our customized implementation of stack as it exists in this thing that we just wrote. But yes, important to note. Thank you, Moonstar. And yes, I see why they taught you guys Haskell now, so that they can scaffold you into abstract algebra. Fun! Yes. I mean, abstract algebra is extremely useful, but I only learned about it in grad school, but, I also did my bachelor's degree in mechatronics, so my bachelor's degree was, a lot of this sort of higher math stuff was conspicuously absent in my undergraduate education, and I had to pick it up later. But anyway, so let's talk about the example that we were actually supposed to be talking about, the birthday calendar. Hopefully this hasn't been too boring for you guys. The birthday calendar is obviously going to be a class. We're going to call it B-Day, because I can't be bothered to write birthday calendar. Object, yes, of course. So the thing about the data that we are operating with right now is we have name and date. We have two different things that are being associated together. These are, if you were to talk about it in more abstract mathematical terms, what you are doing is you are creating a mapping from names to dates, or from dates to names. And that's the thing. Either a mapping from names to dates or dates to names would be acceptable in this case. So obviously we're going to move forward on the assumption that we will be using the Python data structure that is best suited to handling mappings, and that is, of course, the dictionary. The question, however, is what do we make the key, and what do we make the value? Do we make the names the keys or the values, and the date obviously has to be the reverse of that? So the question that you sort of run into is, which one is likely to have more unique values? Is it going to be name or is it going to be date? And given that, do you want the keys to have more unique possible values, or do you want the values to have more unique possible values? And I realize that sentence is terrible, but hopefully I will be forgiven. So if we examine what we know of names and dates, we know that within a calendar year, there are 365 unique dates. Even if you take into account the number of years over which you consider the birthday calendar to exist. Say, for instance, there's nobody currently alive who had a birthday more than 109 years ago or something like that. I would wager, given that there are 8 billion human beings on the planet, that there are possibly more unique names in the world than there are dates. But I'm sure the chat's going to check my math on that. So let's proceed on the basis that name has more unique values. If it has more unique values, then we want that to be the key. Because we don't want... Well, your alternative is to have the key value be the more common thing, and then have you're leaving yourself open to the possibility of having to keep track of a list of values within that. Yes, thank you. Yes, 365 and 1/4 days, and 2 seconds, because we want to include leap seconds. What was I talking about? You don't want a dictionary that has to map to a list of names that are all associated with a particular date, necessarily. Although, well, for one, it complicates the contains method quite a lot, although it does make the birthdays method a lot simpler. So let's proceed on the basis that we're taking names as being the key of the dictionary. So, def, init, we shall take self and nothing else. Self.c for calendar is equal to an empty dictionary. Now let's get rid of let's deal with the trivial ones. Define a method clear, taking only self. Self.c is equal to an empty dictionary. Ooh, here we go. It is estimated that there are roughly 100,000 names per language that are unique, so they have created a range from this lower bound to an upper bound of the human population. Either way, more names than days in a single year. Well, yes, but are there more days than names in 100 years? That's the question. So in 100 years, there would be 306. It would be 36,500 individual dates. We're gonna cap it at 100 just to make the math simple, because we're like physicists. So yeah, it would appear that all of the names, even from a single language group, would blow out all of the possible days. So yeah, the assumption holds. Anyway, so with the clear method, we are basically re-invoking the initialization operation, which is to just reset it to a empty dictionary. In order to add something, we write def add self, then two parameters, name and date. Now, all of you smart little cookies out there will remember that the manner in which you add an element to a dictionary is you assign to that the previously unused key. So self.c at name is equal to date. Fine and dandy. Now we want to do contains. Contains takes self and a name. It's relatively simple. You return, by which I mean return with an N, name in self.c. If you remember back from our time when we dealt with these data structures in explicit terms, we had actual explicit slides on them. The in operation as it applies to a dictionary is polling the keys rather than polling the values. So this should be sufficient. Def birthdays. This is maybe perhaps a slightly more difficult. Self and date. We'll say some variable local to the function x is an empty list. We'll return these as a list for no particular reason. For x in x, that won't work. Y in self.c. Remember, this will give us the keys. If self.c at y is equal to the given date, x equals x plus whatever that name is. Then, once all of that has finished, we will return x, which is our list of names that we have accumulated. Cool. And so this is more or less how you would go about doing it. With respect to the difficulty of this question, this is a question I would consider a no-brainer. This is a sort of warm-up question territory. Expect the stuff on the assignments and tests to be a bit harder. So let's see how we did in comparison to the solutions given in the lecture slides. So first of all, they include a doc string, which is always a good idea. They are also using a dictionary. Self.cal, they're calling it cal instead of just C. The clear function uses the same method that we do. Add uses the same method that we do. Contains uses the same method we do. And the only difference here is that birthdays, they're returning a set of the names rather than a list of the names. However, I would consider that to be a relatively trivial difference, given that, well, I guess it does say the set of names, doesn't it? Oops. Oh well. Well, we can change that quickly. x.add y. There we go. It's just that simple, folks. So yeah, that's how you implement the birthday calendar. So let's move along. We have another example here. The mean calculator. The task is to design a calculator for the purpose of saying mean things to anybody who uses it. 4 plus 4 equals 8, dummy. Har har har. Oop, I've got some questions. It really shouldn't be a set. I know 2 Parkers born on the same day. Ooh. Yes, that's... wow. Well, congratulations to them. Yeah, I agree. It's... what if you had a situation in which there were 2 distinct people, right? I wouldn't recommend using a set, but, you know, that's what the question asked for. Even though it sort of goes against our intuitions. I agree that the question is somewhat stupid. And incidentally, do you guys like my background today? This is a mineral called malachite, which is a ore of copper. I think it looks very pretty. So, mean calculator. The purpose of this is to design a calculator that keeps track of the mean of a collection of numbers. So we're going to do this a couple of ways. We're going to examine this one to death. But let's do a relatively straightforward, intuitive implementation of this particular one. Hey? Class. Mean calc. Inherits object. Define initialization function. We'll take self. So the question becomes, how are we going to store these values? Could you make some orcish armor with that malachite? Well, probably. Probably. It all depends. It's interesting, actually, considering that malachite is an ore of copper. It's interesting, right? Copper has 2 phases. Ha. Ooh, that... well, I mean, I suppose I could. Couldn't I? Yes, so... Moonstar is revealing hidden knowledge of the professor's recreational programmatic pursuits. I'm working on a video game that it's currently in development. It's going rather well, actually. It's a kind of a node-based puzzle game, but I'm not sure that I want to put it on the internet yet, because it's not nearly finished, and I don't want to, you know, give people impressions that they might be fine ripping me off for it or something like that. I do actually intend to make money on it, so probably wouldn't be too good to play my hand too early, but, you know, such as it is. Anyway, so the mean calculator. We have to decide what the underlying data structure is going to be. In this particular case, let's sort of do it intuitively. Imagine that we keep all of the numbers that have been added to the dataset in a list. Since we have the specification at the bottom of the slide, that we definitely want to be able to add the same number multiple times, meaning that a set, pardon me, a set will not do in this particular instance. So, self.c for collection is equal to an empty list. Now, we want 2 methods, only 2 methods this time. Add self and n, and def mean. Don't be mean, folks. Adding to the list is a relatively simple operation. We've seen it a few times even just today. Plus n. You can also use the append method. To calculate the mean, everybody knows that the mean of a collection of numbers is the sum of those numbers divided by the number of things in that set. So, in this particular case, we want to return the sum of self.c plus the, good lord, not even that, length of self.c. There we go. And there we go. We have a mean calculator. So, I'm going to anticipate the slide. You can see we are more or less completely in line with what has been given in the slide here. However, I'm going to anticipate the slide slightly. There's a more efficient way of doing this. And I'd like to take a moment and see if chat can tell me what a more efficient way of organizing this class might be. Oh, yes. Sorry. Yeah, that's a mistake. Self should be passed as an argument to mean. That was my bad. My apologies. I will shave my eyebrows as penance. Not actually. Although I have been considering getting a rather radical haircut because my hair is driving me mad. Yep, it does actually have to be there. I did forget. So the problem that we have with this particular implementation of the mean calculator is that we don't necessarily need to keep a list and occupy all that memory with all of these data points. Yes, thank you, Frankie Yang. You want to keep a sum and length instead of the list. The list occupies a lot of memory. You could just keep 2 integers, as opposed to keeping x integers, where x is the number of things that have been added to the calculator. So let's make a mean calc 2 class that implements that. Define init. Init. There we go. Self dot sum. Well, do we want to call it sum? Let's call it s. Is 0. And self dot n for number of items is also 0. Our add function becomes add self n. We want to increase the value of s by n, and we want to increase the value of self.n by 1. Please note that this is completely legal to have a parameter called n and a attribute also called n. Since the attribute is referenced through .syntax, there's no naming conflict between these. Could you have been mean by... Alright. Could you have mean be a variable that gets set so it doesn't recalc every time? You can also do that, yes. Yep. That would also, yeah, good observation, Moonstar. That would be another way of making this a more efficient solution. So you would, actually, let's just implement that. So self.mean, let's just say, is -1, sure. Or null. Null might be better. Every time we add something, we have changed the data set, so self.mean is equal to null again. I'm kind of discounting at this point the amount of space it takes to save the character string null, but you'll get the idea. If self.mean equals null, then self.mean equals this bad boy, and then you can return self.mean. Or actually, you can save that for the end. Else. Actually, you don't even need an else. What am I doing here? Ha! He's gone mad with power! There we go. That would do her. So yeah, there you go. Oop, Jesus. There we go. Anyway, so you could do that. That would also tighten things up a bit. Probably not worth the effort for mean-calc 2, however, since essentially in this you're performing like one division operation, there's really no point, whereas the sum operation obviously has a complexity equal to the length of the thing that you're summing, so that is, reasonably high. You're improving your best case runtime scenario, but not your worst case runtime scenario. But it's still worth it to increase your best or decrease your best case runtime scenario. Anyway, so once you calculate the mean, self, not going to forget the self this time, you're just returning self.s divide by self.n. And there you go, mean calc 2. And you can see we have, this is roughly exactly what we have in the slides. So, here is a question for you in chat. Please type A or B for yes or no. If only add and mean are used, can MC1 and MC2 be distinguished? And I am here going to define, well, no, I'm not going to. You can take the act of distinguishing between these two to mean whatever you think it should mean. Could you tell the difference? Well, the other purpose of having the mean method would be if you were to make these members private members being a thing that we're going to be talking about very shortly. Look at me, out of frame. Good Lord. Okay. I'm going to assume nobody is saying A or B here. So I'll just give you the answer. The answer is both A and B. From the perspective of functionality, black box functionality, mean calculator 1 and 2 cannot be distinguished from each other. They have the same functionality. However, if you were doing code profiling, you might be able to distinguish the two of them, given that one runs more efficiently than the other. So I have a question. But if you call the mean method again after adding new stuff, the result would be the old one. Not if you reset self.mean to null every time you add something. What about removing a number? See, yes, that's the problem. This is... Okay, thank you, I'm glad you brought that up. So, mean calculator 2 is more efficient than mean calculator 1. However, mean calculator 2 has to make some sacrifices to be able to achieve that. One of the sacrifices that it makes is that you can't modify the data set once you have, begun to populate it. You can only clear it completely if you were to create a clear method. the other thing is that you couldn't. It's conceivable that if you're interested in the mean, you might also be interested in some other statistical information with respect to the data set that you're entering. Something like standard deviation or mode or median and those sorts of calculations. Storing the data in this fashion means that none of those other operations can occur, which, that's the sacrifice that you make by getting this higher degree of runtime efficiency. Whether or not that's a good trade-off, that sort of is up to the designer. So, abstraction. Whereas functions provide functional or algorithmic abstraction, classes provide data abstraction. Classes can be used without needing to know the data structures of the implementation. The documentation refers to the abstract data structures, but that may not be present in the implementation. So this is kind of, the purpose of this is to demonstrate to you, for all intents and purposes, it does not matter how mean calculator has been defined, so long as the only thing that you need from it is to calculate a mean. If you're the person creating mean calculator, then you may have additional requirements on it, but for the purposes of black box design or modularized design, mean calculator 1 and 2 are exactly the same thing, so it doesn't matter. The implementation details do not matter. So, yes. So the next topic that we will talk about on Friday will be hiding methods in members using private notation, and also we'll talk about Mario a little bit, and Larry von Lemming the Koopa Man. So, yes, I am aware of the time, thank you. I will stay on the stream for a few minutes further, just in case anybody has any questions pertaining to anything, really. But other than that, thank you very much. Peace out. Talk to you later. I don't know. I need a catch symbol. Like, Probably. That's stupid. I did actually buy pillows from a gypsy, by the way. I have them right here. They're kind of cute. Don't worry, I sterilized them. I hope that Moonstar realizes he's not getting paid for all of this kissing up that he's doing. Okay. Well, I'm going to call it here. Take her easy, folks. Stay safe out there.